This video shows an experiment conducted by Mike Meyer out of UC Davis where we have a tensile sample. And you're going to notice a couple of things. As he's pulling on this tensile sample, we will see at locations of stress concentration the first plastic deformation, and then it begins to move downward into the reduced section area. And you'll notice that these regions of plastic deformation, which are called Luder's bands, and are at 45 degrees with respect to the loading axis. Okay, it's important that we understand why we're spending all this time talking about Mohr's circle. The reason is actually quite simple. It is because for metals, yield occurs by dislocation glide along slip planes. And this is fundamentally a shear phenomenon. This is a simple animation of dislocation motion from Cambridge in the UK. And so it behooves us to find planes of maximum shear so that we can sort out when, for a given load, we will have shear stresses that would give rise to plastic deformation. And so this is another quick example of a Mohr circle where we have a plane stress element. Now, plane stress element means that the only stresses we have are in one plane. So we have no stresses in the z direction, which would be pointing out of the page right here. Instead, we have a tensile stress of 80, whatever it happens to be, MPa, pointing in the positive x direction. We have a 50, let's just call it MPa, shear stress, and it's pointing downward, which means it's trying to rotate. This stress is trying to rotate the cube clockwise. Up here, y face, all we have is a shear stress. We have no normal stress. When we take this particular element, so if we plot this particular element on Mohr's circle, we know that we are going to have to plot in the normal stress axis, that's this direction, we have to have 80, and then it's going clockwise, that shear stress is trying to rotate clockwise, so we go up by 50, and that becomes a point on the Mohr circle. The normal stress in the y direction was 0, so that's right there. We come down by 50, and that determines the other point on the Mohr circle. We draw a straight line between those two, and that becomes the diameter of our Mohr circle. So now what we can do is we can rotate in Mohr's space by twice some angle. If we rotate twice phi, what we identify is the principal stresses, meaning no shear stresses. We identify an orientation of the volume element, which is shown here on the left, where all we have is normal stresses acting on the faces, no shear stresses. This is called a principal stress state and a principal stress orientation for the particular volume. So that becomes important because there are some materials where failure is governed by maximum principal stress. There are some materials where failure is governed by maximum shear stress, ductile metals. But for brittle materials, the principal stresses can be responsible for failure. So Mohr's circle helps us in a lot of ways, not just for metals. It helps us identify principal stress states, and it also helps us identify planes of maximum shear. So let's go back to this Mohr circle over here. We know that we would rotate by 2 phi in order to clockwise by 2 phi in order to get a principal stress state, and we would rotate by phi over here in the material space to give us that principal stress state. And what we notice is sigma 1 is tensile, that's 104, that comes from this point right there. Sigma 2 is compressive, that's minus 24, that's this point right there. So these are the 2 points that represent the principal stresses of 104 and minus 24 on the materials element. We can rotate counterclockwise from point A, which is this original stress state up here, and if we rotate counterclockwise by some angle we can identify based upon the Mohr circle, we would find the maximum shear orientation, and that is shown in this third little material element down here. So if we rotate from the initial state, which is shown up here, to the maximum shear stress state, which is shown down here, then we find that the tensile stress acting on this face is 40, and the shear stress is 64. We have 40 operating on the other tensile face. The shear stress is 64. So that allows us to easily identify those key stress states associated with various orientations of materials elements inside a sample.